This is a tutorial screencast for Organic Chemistry 1 on the topic of expanding a molecular formula into different structural claims and then ways of classifying them. So in the first example, we're given a molecular formula of C4H10O. So we'll run through a couple exercises here to review the information that the molecular formula is telling us. The first thing we'll do is take the molecular formula and then determine the molecular weight. So we're going to use that from the constituent elements present, so carbon, hydrogen, oxygen, and then let's just use the nominal atomic masses for each of those. So carbon's 12, hydrogen's 1, oxygen is 16. And then we're going to multiply each of those by their proportions. So carbon is 4. That gets us a total of 48 mass units for that molecular formula. Hydrogen is 10, so 1 times 10 is 10. Oxygen is 16 times 1. That gets us 16. So let's go ahead and then add all of those up. So 8 plus the 6, that's going to give us 14. Then we have 4, 5, 6, 7 is going to give us a total of 74 grams per mole. So that's one exercise that's useful to be proficient in. As we carry on through the semester, another way of approaching this problem that we'll learn in Module 2 is if we're given a molecular weight of, say, 74 grams per mole, can then we figure out how to convert that back into a molecular formula. And there's logical ways of doing that that we'll explore. But given the problem here of the molecular formula, we want to take that and start expanding it into structural claims. And so what is the first thing we should do in these type of exercises? So we have the molecular formula. Let's go ahead and calculate the degrees of unsaturation. So for that, we need to use the alkane molecular formula. That's CnH2n plus 2. And the reason we do that is each carbon atom is saturated, meaning that it has 4 sigma bonds. So for any n number of carbons, there's 2n plus 2 hydrogens attached to it. In our case, n is equal to 4. So for 4 carbons, what is the maximum number of hydrogen atoms that could be present? So C4, 2 times 4 plus 2 will result in C4H10. So 4 carbons should have 10 hydrogen atoms. And as we can see from our given molecular formula, C4H10O, that there's the maximum number of carbons there. So because that the max, that basically is telling us there are no degrees of unsaturation. So anything we draw, there should be no pi bonds and no rings. So that makes our life a little bit easier in one sense. So we're just going to draw things that are basically either a linear carbon chain or branched. However, the molecular formula has a heteroatom. So let me color that in red here. So oxygen is a heteroatom. And we're defining that as anything that's not carbon or hydrogen. because our molecular formulas will always have a carbon and hydrogen component. Any other atoms present will be listed alphabetically, and then we call those heteroatoms. So what is the information telling us? We have no degrees of unsaturation, and we have an oxygen heteroatom. So the functional groups that we learned that contain oxygen with 0 degrees of unsaturation those are alcohols and ethers. So anything that we propose either has to have an alcohol or an ether. So functional groups, such as alcohols or ethers, are defined to have a specific bonding pattern. So that name is going to correlate structurally to some specific pattern incorporating those elements. So we learned in class how to start drawing these logically. So we have 4 carbon atoms. Just going to write the number 4 to keep track of things. And let's draw the linear chain first. And then from there, we'll start drawing branched compounds. And we'll put in our 2 header functional groups that we need. So up here in a column, we'll say alcohol. Then over here, we'll say ether. So now what we're doing is taking that formula and then drawing structures here that have either an alcohol or an ether present. And we'll see what are some best practices in doing this so that we get kind of all the possibilities, but then also that we don't repeat anything we've already done. So first things first, we have 4 carbon atoms. Let's draw them in the chain here. So now we have to put in an oxygen. And you'll find that when we do this, we're basically substituting out a CH bond, putting in the CO bond, and then that hydrogen we took out, we're just going to stick it back onto the oxygen, and that makes the alcohol. Let me write in some numbers here on this chain. So 1, 2, 3, 4. The most logical thing to start to draw an alcohol is we have the longest chain. Let's put in an OH group at position 1. So this is an alcohol. It's a 4-carbon alcohol. The OH group is at position 1. So this would be called 1-butanol. So alcohols end in OL. Of the nomenclature, the last little bit of the name corresponds to the major functional group. So OL is alcohol. The number here, 1, is telling us where on that chain the OH group is bonded. So if we're being logical about this, we started at position 1. We could draw another structural isomer where we put the OH group at position 2. And now this molecule is going to have a different name because the OH group at position 2 has to be shown explicitly in that nomenclature. So this is called 2-butanol. Now with that, we've exhausted the possibilities of drawing linear compounds with the longest carbon chain and putting that OH group in. That said, let me draw something here and number the carbon chain so that we understand if we were to put the OH group at position 4, So 1, 2, 3, 4, we put it there. Would this be called 4-butanol? And the answer to that question is no, because all we've done is really just redraw 1-butanol in a different way. So we will see as we progress through the modules the rules for nomenclature that basically state any functional group has to get the lowest possible number on the carbon chain in which it's located. So the OH group is on position 1, so this is 1-butanol. Even though we're numbering this chain this way, and in theory this could be called 4-butanol, that violates the nomenclature rules because that OH group does not have the lowest possible number it could be. So the same thing could stand for why 3-butanol also does not exist in terms of a proper name. So those would violate nomenclature rules. And as I mentioned, they're essentially just redrawing the things we already drew. So those are the linear alcohols. Now, what about ethers? An ether has a carbon, oxygen, carbon bonding pattern. So meaning that when we draw our linear isomers here, so we got to start with carbon, and then we can put an oxygen. So we have 1 carbon, then an oxygen, meaning we have 2, 3, 4 carbons. And so that's the bonding pattern for an ether, where you have carbon, oxygen, carbon. We can also draw another ether where we have 1, 2 carbons, then an oxygen, and then the 2 remaining carbons. At that point, we can't draw any more of that type without either redrawing something we drew or violating some Lewis dot rule. So now let's move down to branched isomers. And when I refer to branched, we're talking about the carbon chain here. So we'll move down to 3. 1, 2, 3. Let's go ahead and number that. And then we have that 4th carbon atom we have to put at position 2, because otherwise if we put it at 1 or 3, we're just going to draw linear isomers, which we already did. So again, we want to be rational about drawing these alcohols. So let's go ahead and put the OH group first at position 1. And so now this is what we'll call a branched alcohol. And if we name it, the major functional group, since it's an alcohol, it's going to be in the parent name. We have 3 carbons, so it's going to be a derivative of propane. And refining that, it'll be a propanol. And then we have this substituent here, which is 1 carbon or a methyl group. So we would name this 2-methyl -1 propanol. We could move on and draw another structural isomer where the OH group is at the 2 position. And so now we would call this 2-methyl 2-propanol. And at this point, we are pretty much done drawing branched alcohols because we can't put those elements in their proportions together in any other way without either drawing something we drew or violating a Lewis dot rule. So what about branched ethers? So we need to start with a carbon and then bond it to an oxygen and then bond it to another carbon. So now we have 2 carbons accounted for. We have to put 2 more in, and then we want it to be branched so that it's a constitutional isomer. So let's start putting in a carbon here, and then we'll add 1 more carbon to it, and that will make a branched isomer. And there's really no other ways that we could combine them that are going to draw any ethers. So we'll learn nomenclature rules for naming these things. But one thing we can point out now for the ethers specifically, if you put your eye on the oxygen and then you look at the groups bonded to it, so on this side there's 1 carbon, this side there's 3, we could say that that ether is not symmetric about the oxygen. In this case here, we have 1, 2, 1, 2, so we could say that's a symmetric ether. This final case, we have 1 and then 3, which is branched, so this would be non-symmetric as well. So within each functional group, there's further ways of classifying things. And we will learn more of this as we progress. An example of that case with, say, the alcohols. Say we wanted to classify our alcohols. If we went through this exercise here, there's the OH group, that's the alcohol. It's bonded to a carbon. So we want to classify that arrangement. That carbon is bonded to 1 other carbon. So we could say that is a primary alcohol. If we identify the carbon here bearing the OH group, that carbon is bonded to 2 other carbons. So we would say that is a secondary alcohol. In this case, the carbon has 1, so that's primary. The final case, the carbon bearing the OH group has 1, 2, 3. So this would be an example of a tertiary alcohol. So alcohols can be further classified as primary, secondary, or tertiary. Based on the Lewis dot structure rules, you cannot form a quaternary alcohol because as we see, the carbon bearing the OH group, that's required to be an alcohol. The maximum number of other carbons it can have is only 1, 2, or 3. So if we dig a little bit deeper and we want to practice, we can go through that exercise of uniqueness. So in green, what we'll do is figure out the number of unique carbons for each compound here. So looking at 1 butanol, and we're gonna run along the carbon backbone. And really the test question is, does this carbon, is it unique? Or as I look through the molecule, is there another carbon that has the same bonding pattern? So I'll put a dot on each carbon that's unique. And if we start at carbon 1, we're starting there, so yeah, that's a carbon. It's got an OH group, 2 hydrogens, and it's bonded to another carbon. We move on to carbon 2 on the backbone. That carbon has 2 hydrogens, and it's bonded to 2 carbons. So it's different from carbon 1, so that's unique. Now carbon 3, it has 2 hydrogens. It's also bonded to 2 carbons. So that's the similar bonding pattern to carbon 2, but it's not the same because its relationship to carbon 1 is different than the relationship of carbon 2 to carbon 1. Stated another way, if you're standing on carbon 2 and you look to the left, you look to the right, you're going to see something different if you do the same test from carbon 3, looking to the left, looking to the right. You see different environments, so that is also unique. And then carbon 4 is a CH3 group, so none of the other groups were CH3, so that has to be unique. So this is going to have 4 unique carbons. Let's do the same exercise for 2-butanol, where we start at carbon 1, that's a CH3 group. We move to carbon 2 bearing the alcohol. It has to be unique because it has an OH group. We move to carbon 3, that's a CH2. It's got to be unique because none of the other ones have a CH2 yet. Now when we get to carbon 4, it's a CH3 group. Carbon 1 was also CH3, but they're not the same because this CH3 group has a different relationship overall to that carbon bearing the OH. So here they're kind of neighbors. Here they're not so much neighbors because carbon 3 is in the middle. So that would also have 4 unique carbons. Let's move down now to 2-methyl-1-propanol. We start at carbon 1, has an OH, 2 hydrogens, and then it's bonded to carbon 2, so it's unique. Carbon 2 is bonded to 3 carbons. It has 1 hydrogen. That's unique. Now, when we branch off from carbon 2 on these different pathways, we have a CH3, a CH3. So they're both CH3. Are they the same type of CH3? Yes, they are, because you walk out here, you look back, you see carbon 2. You walk out here, you look back, you see carbon 2. And no matter what you do on those paths, they all sort of see the same thing. So for these, let me color those in. Maybe we'll use a different shape instead of a circle. We'll call these a little box. So overall, we're going to have 3 unique carbons. Then for the last case, 2-methyl-2-propanol, we start at carbon 1. So we start at carbon 1. That's a CH3 group. We go to carbon 2. That carbon has the OH. It has no hydrogens because it's bonded to 3 other carbons, so that's also unique. But now what about when we branch off? CH3, CH3. Are those unique? Well, not really, because if you stand here and you walk to each of them from 2 to this methyl, 2 to that methyl, and 2 to that methyl, we have methyl, methyl, and methyl. So actually these 3 groups are all the same. And let's change that initial circle to a little box and say that because all of those are the same, we only really have 2 unique type of carbon. So go ahead and then practice that sort of same logic for the ethers. How many unique type of carbon does each ether have? And then to really push your understanding of this, do the same for the sets of hydrogen. how many hydrogen sets does each have, and then what are the ratios of those hydrogens. So for the alcohols, as you're doing that, consider the OH as its own unique set of hydrogen, because it's bonded to oxygen. So therefore, it's got to be different than hydrogen atoms bonded to carbon. So practice that as you go through as well. Practice classifying carbons according to attached hydrogens. We were using those terms methyl, methylene, and methine. So we'll introduce another one of these practice problems, the logic we want to apply, and then we're going to see that the challenge increases quite a bit as we add heteroatoms and then calculate degrees of unsaturation, and how the two of those things can lead to a large quantity of structural isomers we can produce. So now we're going to look at C4H10O. When we look at that, we know there's going to be carbon and hydrogen, but now we have an oxygen, that's the heteroatom. So if we take our molecular formula, we want to figure out the molecular weight. We use the nominal atomic masses times the proportions. And when we add these together now, we'll find that we get 72 grams per mole as the molecular weight. Let's now convert the molecular formula in figuring out the degrees of unsaturation. So again, we're going to use the alkane formula of CnH2n plus 2, where n equals 4. From our prior problem, we found that it's C4H10. So 4 carbons should have 10 hydrogens. So because we have the presence of this heteroatom now, what we have to then do is revise the given molecular formula. So C4H8O. We need to revise it in consideration of how does the heteroatom affect that count. So oxygen, which is in group 6 in the periodic table, does not affect our given hydrogen count. So this actually will then be revised to C4H8. And so now we can do some organic chemistry math. In theory, for C4H10 minus our revised C4H8, we subtract out. Carbon's not going to play a role in how we determine degrees of unsaturation. So H10 minus H8 is H2. And we're going to define a degree of unsaturation as an equivalent of H2. So 2 divided by 2 is equal to 1 degree of unsaturation. And we know structurally 1 degree of unsaturation can translate either into a pi bond or a ring. So embedded within that molecular formula is 1 degree of unsaturation, and we need to propose structural isomers that have a pi bond or a ring. And now the reason this gets a little bit more complicated is the presence of that oxygen. So within the functional groups we've learned, we know that we can have carbon-carbon pi bonds, that's an alkene. But what about a carbon-oxygen pi bond? That's called a carbonyl group. And there are many different functional groups with carbonyls. So even though we have a CO double bond, depending on what is bonded to that carbon, we can then further refine this into specific functional group names. So for this, 1 oxygen, 1 degree of unsaturation, if that's how we're going to use that in drawing things, these can then either be aldehydes or ketones. So the other scenario is a ring. So ring just means a cyclic structure. So for this, we could either have all carbon in the ring. So that's one scenario. Another scenario is include oxygen in the ring. So we have to kind of approach this in a logical manner. And really what we'll find is, because we have all of these possibilities of the information in that molecular formula, we can draw quite a bit of structural isomers here. And then from that, we want to just apply the logic of classifying them in terms of the uniqueness. And that helps us really learn, how can we apply these things to draw stuff? How do we then start classifying them? What differentiates them? And then, as we'll see in Module 2, when we start learning about analytical instrumentation, there's ways of differentiating them using chemical instrumentation. So I'll start off by drawing some things, but I'll leave the rest for you, the viewer, to practice this stuff. So let's say we want to start with four carbon atoms in the linear arrangement. And we'll start initially with some pi bond considerations. So we'll say kind of up here pi bond, and then of that we had the two scenarios. So alkene, where we're going to show the unsaturation as an alkene, or alternatively, if we wanted to show it as a carbonyl, the CO pi bond. How can we then put these things together? So we have 4 carbons, and say we're going to use the red here to number some things. 1, 2, 3, 4. We want the degree of unsaturation to be a pi bond. So say we want to start at carbon 1 and put the pi bond. And so we have the unsaturation in there. So we still have to put the oxygen in there now. So we can do that in a lot of ways, really. So that oxygen, therefore, has to be an alcohol. So if we put it there, it would be on carbon 1. We talked a little bit about assigning priority in terms of double bonds. So notice this relationship as I've drawn this oxygen, how it's on the opposite face of the alkene, which means I could draw another structural claim where I put the alcohol group on the same side. So now it's on the same side. And these would be 2 structural claims for that. We could draw some more isomers. that have the double bond starting at position 1, but then we're moving the alcohol to carbon 2, to carbon 3, to carbon 4. So I'll let you, the viewer, draw those things out. And then once you have those drawn, you could still continue on with these sort of linear isomers with a double bond, but now you start the double bond at position 2. So an example of that, there's our 4 carbon atoms. We want to put the single degree of unsaturation now starting at carbon 2. Now we need to put the OH group in, so let's start at carbon 1. And then you can draw a couple different structural isomers using that logic as well. Say now we wanted to move over to drawing structural isomers where the single degree of unsaturation is a pi bond, but that pi bond is a carbonyl. There's the 4 carbons. Let's number them. 1, 2, 3, 4. And now we want to draw a carbonyl group. So CO double bond. Let's start at position 1. We have the carbon. We put in a double bond. This carbon atom now has a carbon, and then let's draw this hydrogen in, because this is a new functional group. Of the carbonyl containing functional groups, that carbon, which is sp hybridized now, so carbonyl sp hybridized carbon, the carbon is bonded to an H and a C. That's called an aldehyde. We could apply the same logic with 4 carbons. We've numbered them, and now we want the carbonyl group to be at position 2. So this is a different bonding arrangement of that carbonyl. The carbon's sp2 hybridized, but it is bonded to carbon and carbon. So it's not an aldehyde. It's called a ketone. So in these two bonding patterns where the carbonyl, again, 1 degree of unsaturation, that carbon, if it has an H and a C, that's an aldehyde. So an aldehyde will always have the carbonyl at the terminal carbon of the chain. So it has that H. A ketone moves that carbonyl to the internal carbons. So sp2 hybridized carbon, carbonyl, carbon and carbon, that's called a ketone. So even though I haven't formally named these using nomenclature rules, you can tell by the bonding pattern, the carbon at the terminal, sp hybridized carbonyl, that's an H, that has to be an aldehyde. So aldehydes always have that bonding pattern. Ketones will always have the carbonyl internal, so sp2 hybridized carbon, carbon and carbon. So we've seen now in doing this exercise a couple different ways of drawing structural formulas, ways of identifying functional groups, and then what you want to do now to practice is look at each carbon here. How many attached hydrogens does it have? What is the hybridization? What are the bond angles? Do the same thing for our carbonyl containing compounds. We could also then, moving forward from this, We can drop down to like branching now, so where 3 is the longest carbon chain. So you can go ahead and practice that. But before we wrap up, let's do some drawing where the degree of unsaturation is now present in a ring, which means that the ring is going to have that degree of unsaturation, so we can't put any pi bonds in there. So just rings. So we had C4H8O, and now use rings. So say we just wanted all carbons in the ring. So there's 4 carbons. Now the degree of unsaturation is in the ring, which means we have to put the oxygen back in, so it has to be present as an alcohol. Say now we wanted to put the oxygen inside the ring. So we have our 4 carbons, we have our oxygen, the degree of unsaturation is the ring. We have 2, 4, 6, 8 hydrogens. So this is another valid structural isomer for C4H8O. And again, the functional group names for these, this is an alcohol, and then this would be an ether. So you can go through, determine the unique number of carbons, the unique sets of hydrogens, their ratios. Another thing to consider in moving from, say, these 4 carbon counts, we can then move down to make a 3 carbon count ring, or you could move this down to make, now instead of a 5-membered ring with oxygen, a 4-membered ring with oxygen, and therefore you'd have an extra methyl group you have to put somewhere else in. How many different places can it go? Then you could further drop that down from a 4-membered ring with oxygen to a 3-membered ring with oxygen. And then of the remaining elements, where do they go? What positions? What are their uniqueness in terms of carbon and hydrogen? And that's a means to practice your drawing, to make sure that you're not violating any Lewis dot rules, and you're being very thorough and methodic about proposing all the isomers you can. If you wanted to further challenge yourself, what about C4H6O? Figure out the degrees of unsaturation present in that. How many are there? What are the possibilities? What about C4H8O2? Now there's 2 oxygens. What functional groups can we make with that? Start putting in other heteroatoms such as nitrogen or halogens, fluorine, chlorine, bromine, iodine. What are the different ways you can bond these things? And if you want to go even more in depth, any of these structural isomers you propose, can you go on the internet and find their physical properties? So for example, in this alcohol we've drawn, what's the melting and boiling point? What about the ether? If you find that data and then compare it, how does this bonding arrangement of an alcohol versus an ether affect the physical properties? So that's a good way of practicing the material we're learning now. As we move into Module 2, we'll learn about the instrumental techniques that actually tell us the uniqueness concept that we're learning.